All right, this is section 5.1, light and quantized energy. We're going to compare, the objectives we're going to go over today are we're going to compare the wave and particle natures of light, define a quantum of energy, what that means, and explain how it's related to the energy change of matter. And we're going to contrast the continuous electromagnetic spectra and atomic emission spectra. Okay, so we're going to go over all this vocab, and the main idea is that light is a form of electronic radiation and has characteristics of both a wave and a particle. As you're taking notes on this, remember that you can stop and pause the video anytime you want. Okay, so Rutherford's model. This is where we left off with the history of the atom. It's concentrated. He's found that the atom's mass was concentrated in the nucleus and the electrons moved around it. It didn't explain how the electrons were arranged around the nucleus. They still didn't have an idea about that. And the model didn't explain why negatively charged electrons weren't pulled into the positively charged nucleus. Okay, so in the early 1900s, scientists observed certain elements emitted visible light when heated in a flame. Okay, so we're going to do that lab, and you'll see what I mean about that. Analysis of the emitted light revealed that the element's chemical behavior is related to the arrangement of its electrons. Okay, so all the chemistry we're going to be talking about here has to do with the electron arrangement in the various atoms and how that gets changed and rearranged. Visible light is a type of electromagnetic radiation. It's a form of energy that exhibits wave-like behavior as it travels through space. So when it comes from the sun and hits our planet, it travels as a wave. All waves can be described by these characteristics. They all have a wavelength, and that's the shortest distance between equivalent points on a wave. That's usually from crest to crest, the top of one wave to the top of the next wave. Frequency is how many waves pass a point per second. Amplitude, how high the wave is. Okay, so in this picture you can see how all these are related. So you should draw this picture in your notes, right? You have draw a little wave, put the wavelength from one crest to the other crest. We use this little lambda symbol. That's the Greek letter for L for wavelength. Okay, so this is the crest, is the top to the top. The trough is at the bottom point. Okay, so you can measure a wavelength on any equivalent point. The amplitude is from this midline to the top of a crest or to the bottom of a trough. It's the same thing. And this is the origin, the midline part of the wave. So those are the parts of the wave. We have wavelength and amplitude and crest. Okay, all light, all electromagnetic energy, in fact, travels at this incredible speed of 3 times 10 to the 8th meters per second. Okay, and that happens to be equal to the product of its wavelength and its frequency, and it's in this little formula here. C is what we use for light. C is the speed of light, 3 times 10 to the 8th meters per second. The lambda symbol here is the wavelength, and V, we use V for frequency. Okay, so with this relationship, these two, the wavelength and the frequency multiplied by each other, always equals the speed of light. Okay, so what that means is if we have a longer wavelength here, we're going to have a lower frequency. So if this number is bigger, the wavelength is longer, it's bigger, the frequency is going to be smaller. And the opposite happens, right? If we have a shorter wavelength here, if this number is small, then the frequency is going to be higher. So these small waves pass the same point more frequently. These longer waves pass the same point less frequency. So we're going to be doing a little math with this formula here in just a second. Okay, so a lot of the problems you have are going to be calculate the frequency or the wavelength of different waves. Okay, since we know that light travels at this constant speed, it never changes, that only leaves us with two variables in this formula. the wavelength and the frequency. The speed of light is always the same. So you get problems like this. Calculate the frequency of some electromagnetic radiation. And this should have been, that should have been wavelength. That should have been with a wavelength. Okay, so this was, question was worded wrong. Okay, that looks better. Okay, with a wavelength of that. So we want to figure out the frequency when they give us the wavelength. Okay, so frequency equals, this little v here equals the speed of light, and this slash means divided by the wavelength. So we just do this. Okay, so this is why we learn how to do the scientific notation on your calculators, right? Because these come out to be really big numbers. This frequency is usually a big number when we're talking about light waves. Okay, so we do the speed of light, 3.0 times 10 to the 8, divided by the wavelength, this many meters, small number of meters, turns out to be a little over 9 times 10 to the 15th hertz. And hertz is the unit of frequency. Okay, so that's cycles per second, waves per second. The number of waves that are crossing a certain point each second. That's what hertz means. So we do it the other way too, where they give you calculate the wavelength when they give you the frequency or the hertz. So this big hertz here, we want to find out what the wavelength is. Now we use the wavelength, rearrange that to get the wavelength. So we do the speed of light divided by the frequency, gives us this, it should have been in, oops, made a little mistake there. That should have been in meters. Okay, sorry about that. Okay, so this is meters. Okay, so when you're doing, there's probably a little worksheet that you'll have to do on this that has different units for the light waves. Sometimes they're in meters, sometimes they're in centimeters, sometimes they're in nanometers. But to correctly figure out the frequency or the hertz, or whichever way you're going, you got to get everything in terms of meters and hertz. Okay, so the sunlight that hits the Earth has a continuous range of wavelengths and frequencies. And when we break that up with a prism, we get a spectrum of colors. And the electromagnetic spectrum includes all forms of electromagnetic radiation. Okay, so this little chart here shows the different kinds. You're going to have to know about radio, microwave, infrared, ultraviolet, X-ray, gamma rays. Okay, you have to know where those are in relation to each other. And you'll notice that the wavelength up here times this frequency down here always equals 3 times 10 to the 8th. Right? These two numbers, 10 to the 8th. So the visible part of our wavelength is very tiny, very small. Okay, so that's what they're showing here, that the visible spectrum of the light is of this electromagnetic radiation, EM for short, is very small. Okay, so light also has a particle nature. It acts like a particle, not just like a wave. And so very pretty smart scientist, Einstein and Max Planck, he discovered that matter can only be gained or lost in only small specific amounts called quanta. And these quantums is the minimal amount of energy that can be gained or lost by an atom. But it's so small that it seems like a continuous gaining or losing of energy when we observe this phenomenon, but it's actually gained or lost in very small quantums of energy. So Planck's constant has this really small value. This is joules, that stands for energy. So it's times 10 to the negative 34, so hugely small. So this is joules times seconds. Okay, so joules times seconds is what Planck's constant is. Photoelectric effect is when electrons are emitted from a metal when a light of a certain frequency shines on it. So it has to be of a certain frequency. That frequency, as we'll see in a second, is related to the energy of the light. So the light has to have a certain frequency for this photoelectric effect to happen, for it to kick an electron, a photon, off the surface of a metal. Einstein came up with this. Both have, light has dual properties of wave and particle properties. A photon is a particle of EM radiation with no mass and carries a quantum of energy. The photons are what hit our eyes and allow us to see. And these are the equations for the energy of a photon. And this H represents Planck's constant we just had on a couple screens ago times the frequency. So even though these frequencies are very high numbers, Planck's constant is a very small number. So even multiplying a very big number by a really, really small number, the energy from the photon still turns out to be very small. And we can rearrange this formula also. If we know the energy, we can use that to find the frequency. Okay, so there's only two variables here. Planck's constant is a constant. It doesn't change. So we have the energy and we have the frequency. So energy depends on frequency, higher energy. Lower frequency, lower energy. Okay, so light's emitted from a neon sign when electricity is passed to it. The excited atoms emit energy. They absorb energy, and then when they release that energy, they release photons. Okay, and that's what we see. So this is a light from, it's a tube that has hydrogen in it. It kind of emits a little purplish light. If we break that up through a prism, we get these atomic emission spectrum for hydrogen at these certain wavelengths. Now these are nanometers, nm is nanometers, 10 to the negative 9th meters. You get these 4 wavelengths, specific wavelengths that we can see. There's other ones we can't see, but these are the ones we can. The atomic emission spectrum of an element is the set of frequencies of the EM waves emitted by the atoms of the element. Okay, so the atoms emit, you can tell what atom it is by its EM spectrum, atomic emission spectrum. It's atomic emission spectrum, right? This is hydrogen. Each element is unique. Its atomic emission spectrum is unique. Okay, so you probably had to stop and pause that to get the notes down, but that's all we got for